Yes. So the basis really of complex numbers is the idea that we want to find the square root of a negative number. Whoever came up with the idea, if it's a single person or a group of persons, I'm not sure of the history. But up to that point, there were some problems that involved the square root of a negative number that couldn't be solved, and we end up remaining right there. For example, I think I highlighted this to you. Like if uh, you have to solve an equation like this. Solve x squared plus 1 equals 0. Right? So if you do this, you'll have x squared, all right, equal minus 1. And x then is equals to the square root of negative 1 plus or minus, right? And you can't do anything about that, right? So the idea came up that, well, why not give the square root of negative 1 a value? And they said, look, let's define the square root of negative 1 as the imaginary unit, the imaginary unit, right? And that means that, well, okay, you can square root any negative number. No? You can square root negative 4i. Oh, what am I doing? Oh, yeah, let me see it down here. So how do I get, oh, yeah, negative 4. And I guess, okay, it's gone. So how do you, oh, you click there and it's gone. Okay, interesting. The controls are moving around the area. I guess what's happening is Microsoft is fooling around with, for those computer science boys in the class, they're actually fooling around with, the controls being, as I said, it used to be at the bottom here. Yesterday, I found them at the top, and today they're in the corner here, right? Um, and I think they're fooling around with that, and people will give their feedback. Sometimes they ask people to say which one is the best. If I'm to respond to that, I'll tell them I like it to the corner here. It's tucked away in the corner here, not taking up real estate to the bottom or the top. I like it there. Yeah, so the square root of negative 4, you can think of it as, okay, the square root of 4 multiplied by negative 1, which turns out to be the square root of 4 times the square root of negative 1, which is square root of 4 is 2, square root of negative 1. Somebody is saying something? Somebody's asking a question or something? All right. There's probably somebody had their mic on. Yeah, right? So they came up with that idea of the imaginary unit. And then they advance that idea now and say, you know what? Let's hatch this set of numbers that we call the imaginary numbers. So from the imaginary unit, they hatch a new set of numbers called imaginary numbers. Imaginary numbers, right? So they came up with that. And then they built on that and say, look, let's hatch another set that is even bigger than that now. We call them complex numbers. Complex numbers. And complex numbers, they define it in such a way that, well, complex numbers actually, I think I went through this last week with you. It included the real numbers. It included the imaginary numbers. And then outside here, have numbers that, yes, I like how this, I don't have to click on something to move it, right? Yeah. So the set of complex numbers becomes the new universal set. I think in your studies from high school to now, you were treating the real numbers as the universal set of all the numbers you know, right? But now we can change that. We can change that. And we can now say that the complex numbers is another universal set. It's a universal set that encapsulates the real numbers as well as imaginary numbers, right? So they're subsets of complex numbers. And outside here now, outside here, you have numbers of the form a plus bi, right? So this here is what we, uh, uh, it's a complex number that has a real component, and then you have an imaginary component, right? So yes, all real numbers, let's say you have a number like, um, let's say 2, right? So real numbers, even though it's not of this form, it can be written like that. It's like that, right? 2 plus 0i. So it does have that form. It's complex, right? An imaginary number, let's say 2i, it's again like 0 plus 2i. It does have that form, right? Where you have the real part is 0 and the imaginary part is 2i, right? So that's that new universal set now that we have to get used to, right? And with that now you can solve, let's say, quadratics, right? That when you do the calculation, let's take one maybe. Let's take one. Let's say you have to solve something like this. Solve x squared plus x plus 1 equals 0. I want to think that this, I'm not sure. Let me try it. So x then is equals to minus 1 plus or minus the root of 1 squared minus 4 times 1 times 1 all over 2. And you see the kind of trouble we are in here, right? So we end up with minus 1 plus or minus the square root of, what's this? 1 minus 4, which is minus 3 over 2, right? And now we have a way of evaluating this, right? So our answer is going to be minus 1 plus or minus root 3. Well, I'll put the I in front, right? Yeah, right? Just because sometimes if you put the I at the back here, sometimes what happens, some people will do this, and you're not sure where the I is, right? If it's under the radical sign or not. So some textbooks you see would write it like that. Um, you will see there are books that would very well write this, right? They'll be careful. You'll see them write, right? So they might write minus 1 plus or minus root 3i. I've seen that before. But just for safety, that you don't put that radical sign over um, the I, you can put it in front here, I root 3, right? Minus 1 plus or minus I root 3. Yeah. So you see, you can solve. Oh, wait, we left out something. There was a 2 underneath here. What are we doing? Yeah, there was a 2 under there, right? So this you'll break up as um, minus 1 over 2 uh, plus or minus uh, I root 3 over 2, right? As I said, you can write this in front and that at the back too. different textbooks will might very well write it like that, you know. Good. So you get this, right? You get what I'm doing here, everybody? So we now have a way that when we were stuck with, usually when we meet up something like this, we don't know what to do, right? We don't know what to do. So now we have a way of evaluating the square root of a negative number, right? As I think I also told you that um, if you have if you have quadratics, remember we had one earlier, x squared plus 1 equals 0. Okay, if you have to draw this function y equal x squared plus 1, you'll see that it's like this, right? The curve comes through here and go back up there, right? It doesn't cut the x-axis. Because usually it's where it cut the x-axis that is the root, right? Well, because the roots are now complex, it means it can't cut the x-axis anywhere. Right? I think somebody asked me that question last week. Yeah. Good. Now that we are introduced to complex numbers, we know there's a whole branch of mathematics now that um, deal with complex numbers. We have to do addition, subtraction, multiplication, and division, right? So all of this we gotta learn now, like small children. We gotta learn how to do the arithmetic involving complex numbers, right? So I think I gave you some examples too already. So let's say you have to express in the form um, okay, x plus yi. Let's go with that, right? And let's go with some simple ones. Let's say you have to add 2 plus 3i. I'm just giving you an example, like, and 4 minus I, right? So you simply you add the real numbers and then you add the imaginary numbers, right? So you go with the 4 and the 2 is 6, and the 3i minus the I is going to give you 2i, right? Simple as that. Tell me if anybody is having any trouble with that sort of thing. Right? So if you have, okay, you have to do subtraction. So maybe this is one. Let's say you're doing subtraction. So you have 4 minus 2i, and you have to subtract 3 plus 5i, You subtract 4 minus the 3 will give you 1 minus 2i minus 5i will give you what? Minus 7i, right? Simple as that. You getting it? If you have to multiply, you have to multiply. Let's say you go with 2 plus 3i times 4 minus I. You do it the way you would multiply two binomials, 2 by 4, you get 8. 2 by minus I, you get minus 2i. And you go with 3i times 4, well, you get 12i. 3i by minus I, you get minus 3i square, right? And this can simplify to be what? 8 plus 10i. And remember, I square, if the square root of negative 1 is I, then let me put the square root of negative 1 is I. Right? Then when you square both sides, you get minus 1 equal I square, right? So this here becomes, right? And you end up with 8. This will become plus 3, right? And your answer is going to become, come out here, 11 plus 10i, right? Follow?
Yes, sir. Yes, sir. I'm
Yes,
following.
sir.
I'm following.
For a moment, I want to know if there's a class still.
So I was like looking at the tree and I was like, where's the tree? And then I realized the tree just added
Oh,
to the
okay,
eight.
yeah. Okay, yes, yes.
I don't know why I thought the tree just disappeared.
Slumbering. I feel sleepy myself. Okay, division now. Let me do a quick one. Let's say you have, okay, 2 plus 9i over 5 minus 2i, right? Um, Sometimes you'll see that the textbook say, as I said, um, they'll tell you realize the denominator, right? Realize. I think there's a play on the word, right? There's a play on the word. Say, okay, realize the denominator. They mean make real, right? They mean make the denominator real, right? So that's what they'll tell you. Um, so what we do in order to realize the denominator is you multiply numerator and denominator by what we call the conjugate, right? The conjugate of the denominator here, which is 5 plus 2i, right? Over 5 plus 2i. It's like you're multiplying by 1, right? So you take this now and you do the long multiplication, and you're going to get what? 10 plus 49i plus 18i squared. You'll do you will do the necessaries, right? Um, you see this is a difference of squares, right? So you'll get 5 squared minus 2i squared, right? When you simplify all of that, you see you'll get minus 8 plus 49i over 29, right? And you can now write that as minus 8 over 29 plus 49 over 29. I know where all these ugly numbers come from, like that, right? And no matter what, when we're dealing with, let's say, x and y's and all of that, we usually would, we might be tempted to do this, 49 over 29i, and then put the 8 over 29 here, right? And this is not acceptable, right? You know, even though there's a minus sign sticking out there, mathematicians have come to say, look, when you're writing complex numbers, you always put the real part first and then the imaginary part, right? So we don't do this. We don't do this. You wouldn't see a textbook doing that, right? They don't care if that negative sign is sticking out there. We write it, the real part comes first, then the imaginary part, right? And then they have all kinds of, um, if you read it, if you have some time, go into the notes. You can find the square root of a complex number. There's a nice example. There's a nice example in the notes. One of the the notes I gave you, right? Let me just highlight it here.
Wait, sir, before I go, how did
Okay,
you get
okay.
5 to 9i?
4 to 9i. How did I get that?
Yeah.
Well, that's for me to know and you to figure out. Try it and see. Multiply this numerator here, this here by this here. Do it slowly. You will get that. You will get that. Right? You in your own sweet time, you multiply. 2 by 5 is 10. 2 by 2i, that's 4i, right? And 9, this 9 by the 2i will give you what's happening there by 2 2 by 5 is 10. Okay, 2 by the 2 I'll give you 4i. Watch, this 9i by the 5i is what? 45, right? The 45 and the 4 give you 49i, right?
I
Yeah,
thought you do some, I don't know. I thought it was
yeah.
just, yeah,
Um,
I noticed I had 3, so I thought I knew you add something, but I was like, this is the first step?
okay, okay. Yeah. All right. Yeah. Let me just do this one. This maybe so let's say you want to find the square root. Find the square root of 15 plus 8i, right? So you're finding the square root of a complex number, right? So what we'll do, we'll say, all right, let square root of equal, right? We don't know what it is, right? So if we square both sides, we'll get 15 plus 8i will be equal to a plus bi square, right? Good. So when we expand this out, you're going to get, all right, this side is the same thing. You're going to get a square. Um, I know you'll question this too. You think you know where I got him? How I end up with a minus here?
No.
I'll give you a clue. You see there's a bi here, so you'll end up with a bi square,
Oh.
right? Somewhere down the line, right? And you will end up with okay, b square I square, right? And remember this I square is -1. So the thing will become minus b square, right? That's where you got that from. Right? I'll do like the textbook. I'm gonna kind of jump some steps. So you have to be a more active reader, right? You understand? You have to think, well, where did this man get this from? Let me multiply this thing and prove him wrong, right? And then you find, oh yes, yes, yes. Right? If I tell you everything, you're not gonna do any thinking. I mean, you're already not doing any thinking. God knows where everybody is in the class, right? They're here and actively listening, doing note taking, and all of that, right? So I want to go down that line again this afternoon. I'm done with that. Yeah. Where were we? Yes. So now that we have this is equals to this, right? And if these two complex numbers are equal, then the real components and the imaginary components have to be equal, right? There's this thing about when two complex numbers are equal, their components are equal, their corresponding components are equal, right? And therefore, we can say this, right? We can say this then that um, a square minus b square is equals to 15, and 2ab is equals to 8, right? So watch this here. This is the real part, equal to 15. And this is the imaginary part, it's equal to 8, right? So you now basically have, it's a pair of simultaneous equations, right? Um, so you can do the algebra now. We can do the algebra. Can I maybe push up this so like this? So we got to solve that, right? So simple. From our equation one, equation two, maybe, right? So simple. B is equals to um, you can see that, right? 8 over 2a, which is 4 over a, right? And then you put this now in here, right? Put that in here. You have a square minus, okay, substitute 4 over a for b in equation one, right? And you end up with a square minus, okay, 4 over a square equal 15. And I'll kind of jump over things here a little, right? So you square everything, and you have a square minus 16 over a square equal 15, right? Multiply throughout by a, you have a to the 4 minus 15 a square minus 16 equals 0. Yeah, you see how we get it? Anybody see how we move from here to here? You multiply everything by a, right? So you'll have, all right, let me do here. A to the 4 minus 16, right? Um, equals to 15a squared. And you do some rearrangement and you get this, right? See that? So what you have to see here, if you watch it good, um, think of it like a quadratic, right? Think of it like, okay, let r, if you're not able to figure it out, let x be 8 squared, right? So if you watch this thing here good, it's like x squared minus 15x minus 16 equals 0, which will factorize to be x minus 16 uh, x plus 1 equals 0, right? And if you replace back the x, you'll have what? A square minus 16, a square plus 1. Just give me 1 second. Yeah, yeah, right? So we solve this now. We solve that and that, right? Um, move this aside. So you solve this, all right? It's either what? Um, a square either a square minus 16 equals 0. So you can see that as a difference of squares, right? So a is equals to uh, plus or minus 4, right? And then a square plus 1 equal to 0. If you try to solve this, you get a is equals to the square root plus or minus of -1. But remember, a is a real number. A is real. A is real. So a can't be that, right? A can't be that. So we're not going to pay attention to these are invalid solutions, right? We're going to use this now, right? We're going to use a equal positive or -4. And I think earlier we had what? B is equals to, yeah. What did we have B equal to? 4 over A, right? 4 over A. Somebody mic their answer. You have to, um, all right. Somebody mic is on. One thing, they're not in front of the computer, so oh gosh. Uh, I don't know whose mic is that. When you're not conscious of it. So it's off. All right. I hope so. All right. Good. Yeah, we're yeah. So we got B equal 4 over A, right? And we got A being either +4 or -4, right? So B then, when A equal 4, B will be equal to 4 over 4, which is 1. When A equal -4, B would be 4 over -4, which is -1, right? So our two values, you end up with two values, right? You end up with two values. You end up with 4 plus I, right? Because remember, it was A plus BI, right? A is 4, and one value for B when A is 4 is 1. And the other value when A is, what was the other? -4, B is -1. So you, oh, sorry, I have to, and when A is -4, B is also -1, right? So you have minus I. So your two square roots, you have two square roots, right? So you can write it as plus or minus 4 plus I, right? The plus will give you that, the minus will give you this. Yeah, so it's a tedious process. I didn't want to highlight, I didn't want to do this. I wouldn't, you know, it's a little more complex than, you know, the very simple addition, subtraction, multiplication, and division, right? This example is in the reading, right? In the notes I gave you. Right? There's even like, okay, they give you the roots of a quadratic, and you have to find the quadratic, right? So how do you know the quadratic? Right? I'll allow you to do some extra reading with that. So, you know, like for example, if I tell you the roots of a quadratic are, let's say 2 and 3, 2 and 3, right? Right away, you know that the equation is really x minus 2, x minus 3 equals 0, right? And you can multiply that out. Well, what about if you were given the roots of a roots of a quadratic, and it's not a nice number now, right? So the what am I writing? Quadratic, right? Let's go with 1 plus I and 1 minus I, because they occur in conjugate. How do you get get back the quadratic? right? Follow this, what I'm doing here, and we're going to see how you get through with that, right? See if you can get the quadratic. And if you want to know if you're right, simply solve back the quadratic and you should have this as the answer, right? You should have that as the answer. Good. So one last thing I want to show you with complex numbers is how do we, as a matter of fact, they actually said, look, we're going to even represent a complex number on a diagram, right? Just like how you can represent a real number on the number line, right? Well, complex numbers can be represented on a graph as well, right? And they call that something called the Argand diagram, right? The Argand diagram. And I think there's a D here, Argand. Yeah, the Argand diagram, right? So if you have a what they do, okay, instead of having X and Y, so they say that okay, this here is the real line, right? And this axis here, the vertical axis, is what we'll call the imaginary axis, right? So if you have a complex number like 3 plus 2i, and you plot the real, I say, okay, down here is 3, and down here is 2. Well, then down here is that complex number 3 plus 2i, right? In some textbook, they'll actually draw a line. They'll actually draw a line from the origin to that point, right? So if you have another one, or let's call this Z1, let's call Z2, it's 4 minus 5i. Okay, so you go with 4, or let's say 4 is here, right? And minus 5 is somewhere here, right? So here is the complex number 4 minus 5i. And as I said, in some textbooks, you see them drawing a line. They draw a line connecting the origin here, the origin, to that complex number, right? So, and what you can do now, you can actually add and subtract complex number that way as well, right? You can add and subtract complex numbers the same way you add and subtract what you call this thing, vectors. You all did vectors in high school, right? You can actually add and subtract vectors, right? Um, sorry, you can add and subtract complex numbers, right? So what you could do, watch, let's say, all right, you add these two, right? Add these two. Z1 plus Z2. We'll get what? 3 and 4 is 7. 2 minus 5i is minus 3i, right? And if you were to put that in our graph, where is 7? Okay, let's say 7 is still out here somewhere, right? 7 is here, and minus 3i is going to be somewhere, let's say somewhere, right? Minus 3. So let's go, right? So this is Z1 plus Z2, right? That's the sum of the two. Let me see. 7, yeah, 7 minus 3, yeah. right? So you can actually add, subtract, right? And that sort of thing. Because, so as I said, some conceptualize the complex number with a straight line from the origin to the complex number. I just want to go over here a little. They came up with the idea of what we call the modulus, right? The modulus of a complex number, right? So if you have a complex number, a plus bi, the modulus, they write it like this. The modulus, they put a kind of bracket around it, and that is equal to the square root of a squared plus b squared, right? And this is really the length of the line segment. If you were to have some complex number, let's say it's here, it is that the length of the line segment from the origin to this complex number z, right? You say z is equals to this, right? So the modulus of z is equals to that. So the length, this length here is the modulus of z, right? I went a little further and say that, okay, this angle, the angle that the complex number makes with the real axis, right, is going to be given by tan inverse, or theta is equals to tan inverse of b over a, right? It's going to be given by that. And they give it a name. This angle is called the argument. If you do that, it's going to be left on the screen and the whole thing is going to be messed up now. So they give this angle a name, right? And they say the argument of z, right? The argument of z is equals to tan inverse of b over a, right? So they actually, you actually can now say that the complex number, it has a modulus, and it has some sense of direction, right? Because you can now say what is the angle that it makes with the real axis, right? Usually the argument is given a value. The argument of z, it's usually between theta is usually between minus 180 and 180 degrees, right? I don't want to get into it's what you call the principal argument. The principal argument, right? Is that angle that it will make with the real axis. Because if you have one down here, right? Let's say you have alpha there. This angle is going to be a negative angle. I'm not going to get into it because you all haven't done any kind of trigonometry that has to do with negative angles and so. So I'm not going to scare you with that, right? I'm not going to scare you with that. But usually you express the angle that a complex number makes with the positive real numbers, right? And it has to be between these two angles, right? Because even if you have a complex number there, this angle is going to be still less than 180. If you have a complex number over here, this angle is going to be less than, sorry, I should say, it's going to be greater than minus 180, right? So you will find that you can always write down the argument of the complex number between this range here, minus 180 and 180. right? I know you haven't been introduced to negative angles, so I'm not gonna spend any kind of time going out of what you have to do in this particular um, course, right? I'm just awakening you to what's out there. Good. Um, so what we'll do now, we'll pause here. I'll stop the recording. Yeah.